Hi, almost exactly a year ago I reviewed a ZT-702S meter from Zotek, and that meter has a 10 MHz oscilloscope and a 10,000 counts multimeter built in. There were some minor issues, but overall it is a surprisingly capable meter. Zotek seemed to have upped the ante quite a bit with their new ZT-703S. The specs are quite impressive compared to the 702S. For example, the multimeter now has 25,000 counts, and the oscilloscope bandwidth has been increased to 50 MHz. And instead of just offering a single channel, the ZT-703S now has two input channels. And like its predecessor, the 703S is also very affordable. Banggood provided me this meter for me to review. As usual, I will leave a product link in the video description below for those who are interested in getting one after watching this video. Here I have the 702S and the 703S side by side. And from a glance, the only major difference you can see is the screen size difference between these two meters. For the 702S, you can see we have a 2.8-inch LCD, and the 703S has a 3.5-inch LCD. So the LCD is definitely a lot bigger here, as you can see that. And everywhere else, you can see that they are pretty much identical between these two meters. Of course, the 703S has one extra input channel for the oscilloscope and does feel slightly heavier than the 702S. The box the 703S was shipped in is this rather generic one. You can see it's a little bit bent out during the shipment, and there's no marking of the 703S anywhere on the box itself, except on the side you can see we have two versions. One is the single channel, the other one is the dual channel. The meter came with a soft instrument pouch. Besides the meter itself, you also get a couple of these P2060 oscilloscope probes. They are rated for 60 MHz. Now, one of the oscilloscope probes I received was actually not in the pouch itself, but was shipped in the box. So I wondered if the extra probe was provided by Banggood, or it is part of the ZT-703S. Of course, you also get these multimeter probes. They are relatively soft. If I remember correctly, the 702S actually came with a thermocouple as well, and we don't have it here. I'm wondering if the 703S actually omitted the thermocouple measurement mode. Haha! If you look at input jack here, you will see that on the 703S, we don't have the thermometer symbol, whereas we have that on the 702S. So I guess they have removed the temperature measurement function from the 703S, but I wonder why. Anyway, you also get a USB cable, by the look of it, a QA sticker, and of course, a user manual in the pouch. Stop testing voltage in current mode. I absolutely love the warning over the current input jacks. I wonder how many people have done that. Anyway, so this meter is definitely geared towards hobbyists. Let me remove this. Alright, it's time to power it on. It boots into the oscilloscope mode by default, and that was actually almost instantaneous. Now let's actually power it on again, and together with the 702S. Let me power it off so we can do some comparison here. So let's do it together. And you can see that both are pretty fast, and the boot up time actually is very similar. And if I have to guess, the 703S is actually slightly faster. Because the LCD is recessed and not flush with the top of the screen, you can see at an angle, actually you can't really see the bottom menu here. You can see that it fades away when I tilt the screen here. And it's more pronounced on the 703S because this has a larger screen, and I think it's probably closer to the edge as well. So just something to pay attention to. But in typical use, if you are just steering from the top, I don't think you'll run into any issue here. One gripe I had with the 702S last time, if you remember, is that it doesn't remember your last mode selection. For example, if I change it to multimeter mode, next time I power it back on, it will power into the oscilloscope mode. So actually, let's check that with the 703S to see if they fixed the issue here. Now we're in multimeter mode, and let's power it off. And let's power it back on. Aha! So we're back in the multimeter mode. Looks like Zotek had addressed that issue, and it remembers your last instrument selection now. Excellent. Alright, now let me put in a test signal from my O1DG2070 and explore a little bit more. And it looks like the screen just turned off. I'm wondering if there's some kind of a timeout setting. And let's press it. Yeah, it turned back on. And we'll take a look at that setting a little bit later. Now, one thing interesting is that the input jack is a little bit of unconventional, the layout. You can see here, the channel 2 is actually on the left side, channel 1 is on the right side, whereas your typical scope, the channel 1 is on the left side. So that's something interesting. Anyway, just wanted to point out. Let's actually now output a signal. Oh, by the way, this signal generator is, this is really annoying. Now it just turned off again. And this one currently is outputting from channel 2. Let's actually switch to channel 1. And we're doing 2 volts peak to peak. Let's actually change it to, let's say it doesn't really matter, but let's change it to 1. And let me enable the output here. And let's do a auto acquisition here. That is pretty quick, but amplitude looks like on the low side here. So let me actually turn off channel 2 and try it again. So to do that, I'm going to come here, channel 2 off. As you can see, the control is very intuitive here. And let's do another auto range. Yeah, the auto range doesn't seem to work that well. You can see that now the amplitude changed, but the offset also changed. For some reason, it's not able to center the signal automatically. You can see that from our signal generator, right now the offset is actually set at 0 here. So let's actually change to a different frequency and see if we have the same issue here. Let's change it to 2 kilohertz, and let's change the amplitude to 2 volts, and let's try auto ranging again. It looks like we definitely have some issue with auto ranging here. So let's do 1.5 volts and try it again. For some reason, it recognized the frequency with no problem, but the offset is definitely having some issue here. Let me power it off and back on again, see if we see any difference here. It's kind of odd that it doesn't center the signal here. At least we remember the prior setting here. That's actually good. So let me actually reacquire the signal here. Nope. You can see that we definitely have some issue with this auto acquisition here. All right. For the time being, let's just manually adjust the signal here. So let's move it to the center here. And let's actually take a look at the measurement, as we right now have a 2 kilohertz signal coming in. Cursor, let's see here, actually let's go to manual. Let's see here. I wonder if we change the coupling to AC would change the auto ranging. Let's do it again here. So now we're AC coupling, and we're doing auto ranging. The AC seems to actually be fine. Anyway, definitely there's some minor issues with the acquisition here. So let's take a look at what we got here. And I want it to display some measurements here. Let's do, in this case, I wanted to see the frequency, and I wanted to see the voltage peak to peak. Sorry, that's not a frequency, that's a frequency counter. Let's do the frequency here, and that should be it. Okay, so let's go back to how do I get out? Oh, I see there's a measurement exit. Okay, let's press that. And you can see that we have the peak to peak and frequency. Of course, right now we're at times 10, so the peak to peak is 10 times actual output here, but everything else looks correct. This is definitely a very basic scope, doesn't have all the bells and whistles, but you can see that we can also do cursor measurement, no problem. Of course, you can move it around and do the settings. We're not going to do here, but nevertheless, that is the capability of this meter here. Now let's actually try to find out if the claimed 50 MHz bandwidth is accurate. If you recall, the bandwidth of the 702S is 10 MHz, and that one actually meets its bandwidth claim. And for that, I'm actually going to add a 50 ohm termination here so that the measurement will be a little bit more accurate. Of course, the amplitude had changed because we have now added a 50 ohm termination here. So actually, before we put in this 50 ohm termination, the measurement showed 30 volts, which is roughly twice as the output from the DG-2070, but right now it's actually matching because the 2070 is set to have an impedance of 50 ohm output. I just changed the output to 1 volt so that we can see that 3 dB bandwidth a little bit more easily. Anyway, now let's change the frequency here. So frequency, and right now we're at 2 kilohertz. Let's do all the way to 1 megahertz to begin with. So let's do that. 10 kilohertz, 100 kilohertz, and 1 megahertz. We shouldn't have any issue. Right now it's 1 meg. And you can see that we're at roughly still 1 volt. Of course, there is a 10 times attenuation. Let me auto-acquire that signal again. And you can see the auto-acquisition is pretty fast. Now let me increase it to 10 megahertz. We shouldn't see any problem, but it already dropped to, the bandwidth limit here. And let's auto-acquire here. So at 10 megahertz, we're showing roughly 90% of the amplitude. That is actually okay, and let's keep increasing. 20, 30, 40. At 40 megahertz, you can see we are actually having some funny business going on here. And it's having trouble acquiring that signal too. Wow. And you can hear the relay clicking, and definitely we're not able to auto-acquire that signal. So let me, that is interesting. It eventually acquired the signal, but it was not able to measure anything. As you can see, there's definitely aliasing going on. So let's go back to 20 megahertz and see if we can auto-acquire that signal. Yeah, 20 megahertz, there's no problem. But anything beyond that, let's say 30. 30 is still fine. 40, definitely you can see that we are not able to measure that signal cleanly, and let alone 50. So the claimed bandwidth, there's definitely some issue. I would say 30 megahertz probably is its maximum. Actually, let's go a little bit beyond 30, 1 megahertz at a time. 31, 32, 33, 34. Yeah, 33 megahertz is where I would draw the limit, not 50 megahertz. But again, for an oscilloscope of this price range, even 30 megahertz is quite impressive. So let me go back to 30. Let's actually enable the other channel to see if we have any impact on the bandwidth here. So go to manual, let's go channel 2 and turn it on. Yeah, it doesn't appear that the additional channel impacts the input bandwidth here. So you can see here we're at 30 megahertz and we can increase to 40. Again, we see the same problem. So it does seem that the channels are fully independent. That's good. So let's turn the channel off. Here I just captured a amplitude modulated signal. The carrier frequency is 1 megahertz and the modulation frequency is 1 kilohertz. Right now the modulation depth is at 100%, and you can see we captured the signal with no problem. And here we're looking at a frequency modulated signal. You can see how fast the update rate is. Currently, the modulation frequency is at 100 Hz with a frequency deviation of 100 kHz on top of a 1 MHz carrier signal. I was just playing around with the manual settings here. Looks like we also have this display mode. We can change it to XY display as well. I was actually wondering that whether or not we can support XY display, as this is a dual channel oscilloscope. Looks like we can. So let's actually give it a go. Well, I have set it up to display the Lissajous figure. As you can see that we sort of can display it, but the update rate is not that fast. And it doesn't seem that the time scale impacts the display. For example, if I'm increasing it, you can see that it's the same. I'm decreasing it, it's also the same. But nevertheless, you definitely can see the Lissajous figure here. If I adjust, for example, the channel 2 frequency, right now both channel 1 and channel 2 are at 1 kHz. If I adjust channel 2 to 2 kHz, you can see that we definitely can see that Lissajous figure here. And if I adjust to 3, you can see that as well. So let's actually adjust to a fraction here. Yeah, it's right now it's 1.5. You can see, yeah, you can sort of see it, but the update rate is very slow here. Okay, I think I finally found the setting that controls the backlight duration that automatically turns off the backlight, and you can see here is set to 120 seconds. I can turn it off, and now hopefully the backlight will stay on. As we mentioned earlier, the ZT-703S also offers function generator capability. Now, I played around. It seems that the functionality is really rudimentary. As you can see that the output is actually through the standard calibration port on the side here, and by default, it is outputting a 1 kHz square wave, which is what we're expecting here. The waveform you can see is a little bit noisy. I'm not sure what is going on, whether or not it's the contact or it's just DDS, and there's probably some issue with output filtering, but nevertheless, we have this 1 kHz signal right now, and you can see here on the output setting, we can change it on. And right now we're outputting this square wave signal, and interestingly, the frequency is not shown. Let's press the menu button, and you can see we can change it to, let's say, a pulse signal, a sinusoidal, and we press the menu again, and we can actually set the frequency. So let's see whether or not we can change the frequency. Here is a 1 kHz. I probably have to press menu again. Yep. We can change it to 2 kHz. By the look of it, it's really just some discrete values here. So let's change it to 2. And I think I have to press the menu again. Yeah, you can see that we are able to change that. And how about the amplitude here? 2.5 volts. Let's see, 1 volt. Yeah, also is discrete value here. So let's do 1 volt. Okay, so that does work. But nevertheless, it's fairly rudimentary. And of course, if we change, for example, here to pulse output, pulse output, I would expect we can change the duty cycle. Yep, you can change the duty cycle. Is that continuous? Let's see. 50? No. Essentially only a few discrete values as well. Anyway, so that is what you get here. And of course, output can also change to triangular waveform. And you can see that. So yeah, so you can use this in a pinch as your function generator, but just keep in mind the functionality is quite limited here. So by the look of it, the maximum voltage you can get is 2.5 volts. And what is more interesting is actually we have a separate menu item. You can see here more apps. If I press that, you will see we actually have a generator. So I'm actually not sure what is going on here. Why we have two different menu items for pretty much the same thing. But anyway, here, let's see if we have the same parameters to play with. We can increase the frequency and decrease the frequency. And you can see that below 1 kHz, we are able to adjust it 5 Hz at a time, but this is not going to be very useful. Nevertheless, it's more adjustable compared to the other function gen that we saw on the other separate menu item. So it almost seems like two teams are actually working on this functionality, and then they did not talk to each other and ended up with this kind of two separate functionality on the same meter. I don't know what is going on here. Anyway, so as you can see here, let's change the voltage. Can we change the voltage here? See, on this one, I don't think we can change the voltage. That is really odd. But we can probably change the frequency. Yeah, it seems we have the same ability to change the frequency under 1 kHz by 5 Hz at a time, and above 1 kHz, 1 kHz at a time. But now we lost the ability to change the amplitude. So that's very odd. Similarly with the triangular waveform and a couple of others. Very interesting. Alright, next, let's take a look at the built-in digital multimeter. The first thing I want to show you are these stock leads. And if you take a look, the quality is definitely above average. Sure, the leads are not as soft as some of the silicone ones, but if you take a look at the actual tips, these are actually gold-plated. Not sure if you can see, and they're very sharp. So definitely pretty good quality here. The first thing I would like to do is to verify the DC accuracy here. So for that, I'm hooking it up to my MV216A voltage standard, and we'll take a look there. And the current range is the default DC voltage range. So let's ramp up the voltage output here. 1 volt, 2 volts, And the rated accuracy is 0.005% plus 3 digits. And from the current measurement, it's just within that accuracy range. All right, let's increase it 3 volts. And now, as expected, we lost a digit. That's because this is a 25,000 counts meter. 4, 5, 6, 7, 8, 9, 10. No issues. While we're still hooked up to the DC voltage standard, let's actually take a look at the dedicated millivolt range here. And before we do that, let me actually switch the DC voltage standard to the millivolt output. Let's change to millivolts. And in this range, we actually have a resolution of 1 microvolt. Now let's take a look to see if we can actually register that 1 microvolt change. I'm going to increment it by 1 microvolt. Not showing up. 2, 3, 4, 5, 6, 7, 8. Right now we're at 8 microvolts. You can see that the last digit started to show up. Even though this meter has a resolution of 1 microvolt, it's not able to distinguish when the output voltage is below a certain threshold. 9, 10. So let's do that 10 microvolts at a time. 10, 20, 30. Yep, as you go past 10, I think it's actually started registering with no problem. 40, 50, 60, 70, 80, 90, 100. All right, let's do that 100 at a time. 0.1, 2, 3, 4, 5, 6, 7, 8, 9. As you can see, as we're approaching 1 millivolt, it's getting more and more accurate. And this is actually pretty impressive, as most meters cannot offer this level of resolution. So this is 1 millivolt. In this range, the highest you can measure is 250 millivolts. So let's actually take a look at a few other measurements here. This is 2 millivolts, 3, 4, and let's add a 10 millivolts to that. 10, 24. So after you go past 25, of course we have a little bit of wiggle room here. 26, and you can see that we change it to 2 digits instead of 3 after the decimal. The bar graph update speed is really slow. As you can see, I'm adjusting the output from a variable power supply, and the bar graph is jumping all over the place as we are changing the output value, but it definitely is not able to keep up the update rate. Now we're in resistance measurement mode. Let's short out the leads. And you can see it's relatively okay. It's not the slowest, it's not the fastest, it's okay. But we don't have a rail button and we cannot rail out the reading here, but it's pretty close to 0. So the first resistor we're going to measure is a precision 100 ohm resistor, and let's take a look. And of course, because we can't rail it out, there's not too much point, but let's take a look. And yes, you can see that we're getting there, and of course we have some offset, so this is largely a 100 ohm resistor here, and speed is reasonable. And here is a 1K resistor. The speed is actually okay. Alright, let's switch it to continuity. The reading is definitely latched, but it lags a little bit. As you can see here, when I release the probes, it's still beeping, And if I'm trying to continuously hitting it, you can see that it is all blurred together. But given the continuity of speed, it is really not an issue at all. Alright, let's see what's next. Next is diode mode. As usual, let's start with the silicon diode. No problem. And here is a red LED. No issues. And finally, let's take a look at the white LED. And you can see that we are actually able to light it up and also measure the forward voltage drop. Very good. Moving on to capacitance measurement mode. And the first capacitor we're going to measure is this 100 nanofarads capacitor with a nominal value of roughly 75 nanofarads. And you can see that no problem. In the capacitance measurement mode, the maximum capacitance you can measure with this meter is 99 millifarads. So let's actually move up directly to a 15 millifarads capacitor here. So you can see we have this relatively large capacitance capacitor, and let's see if we can measure the capacitance. As you can see, the measurement speed is definitely on the slow side. But we eventually settled down to roughly 14 millifarads reading. Now we're in AC measurement mode. In this mode, the specification says it's able to measure frequency between 40 Hz up to 1 kHz. And right now we're outputting a signal from DG2070. The voltage is 1 volt RMS and the frequency is 40 Hz. As you can see, we're measuring the signal with no problem. So let's actually reduce the frequency. So now we're doing 30 Hz, no problem, 20, 10, and it seems that we can go well below the 40 Hz minimum specified frequency. Alright, how about let's go up. Now it's 100 Hz, and let's increment 100 Hz at a time. 2, no problem. Let's just go straight to 1 kHz. And now we're at 1 kHz. You can see that we are able to measure the input signal. And let's stretch that a little bit. 1.1, 2, 3, 4, 5, 6. Yep, it started dropping now. 7, 8, 9, 10. But it seems that at 2 kHz we're still able to measure that input signal. Keep increasing. So let's see at what point is our bandwidth limit. Now we're at 3 kHz. You can see the voltage reading dropped to the 3 dB bandwidth. So the frequency response specification is fairly conservative. Now moving on to current measurement mode. And you can see the warning sign briefly popped up telling you where to plug in your leads. Now, of course, if you don't pay attention, you wouldn't see that warning. In my opinion, it would be better if they actually just simply remove this bar graph, as we mentioned earlier. It's just useless, and use that real estate to print out where you need to plug in your leads in the current range. And some other meters, for example, the Handheld multifunctional device does that, and that certainly is a nice touch. And if you recall, when I reviewed the 702S, one issue I found was that in the current range, it can give you erroneous readings if you are not careful with which current jack you currently have your leads plugged in. So let's actually take a look to see if we still have that issue here. And for that, I'm going to measure this 100 microamp current standard, and let's put in the current range here. So I'm going to put in the milliamp range. And right now, the range is actually in amp range. So let's actually take a look without changing the range here. Nope, you can see that we still get the same issue. Right now it's showing a 10 milliamp current reading, even though we're measuring this 100 microamp current source. So let's change it to milliamp. And you can see that reading is more or less accurate. But unfortunately, if we are in the amp range mode, you can see that the reading is no longer accurate. This is rather unfortunate. As I mentioned in my 702S review video, the easiest way to address this is to have a separate signal path to the ADC input from these two different current ranges. This way you can switch on and off the specific path depending on the range you are currently in. Anyway, time for us to open it up and take a look inside. Alright, I just opened it up, and you can see the construction is actually fairly decent, as the screws have these metal inserts. Before I do anything else, I do want to take a look at the current consumption of this meter. Alright, let me power it on. And you can see in multimeter mode we're drawing about 200 milliamps. And now this battery is a, let's see, it's a 3.4 amp hour battery, so that would last you about 17 hours. And let's change to the oscilloscope mode. And you can see we're drawing 300 milliamps, so that will last you about 11 hours, and that should be plenty of runtime. At first glance, I'm a little bit disappointed, as you can see that all the major chips, the markings had been etched off. We don't have any markings on this DMM chip, and we don't have any markings on these chips either. So I'm not sure what the deal is, but they definitely don't want you to see what exactly they're using. Let me actually take the mainboard out. I removed the circuit board from the case and desoldered the shielding cans, so we can see things a little bit better. On the left side, that is our input section, and on this side you can also see the ADC right here. Again, unfortunately we don't know what ADC they used in this meter, as the markings had been etched off, just like pretty much all the other ICs we have seen. But according to the manual, the ADC has a sampling rate of 280 megasamples per second, and according to our tests earlier, it seems that the sampling rate is independent of the number of channels enabled. And towards the top here, you can also see a couple of these trimmers. Those are used to adjust the frequency response of the input channels. Interestingly enough though, they chose this kind of plastic BNC input jacks instead of the ones with metal casing. Now, there is a shielding can over the entire input section, but there would be crosstalks between the two adjacent channels, and plastic casing definitely does not help. Of course, this is by no means a lab-grade instrument, but I just wanted to point out the potential issue here. And if you look at the back side, you will see again there's not a whole lot going on in the input section here. But again, the markings had been removed from both of these chips. Presumably these are some kind of mucks, given the typical input section design of these cheap oscilloscopes. So not entirely sure why they bothered to remove the markings of these chips at all. And here is our main microcontroller. Again, we don't know exactly what they're using here because of the marking on this chip had been erased, just like the other chips. But we can tell that this chip is actually doing a lot of the work, as it's not only driving the UI, but also it is actually driving the LCD. You can see here is the LCD. I don't see any additional circuitry on this LCD, and I assume it is driven directly by this microcontroller. With all these markings removed, it seems that Zotek really doesn't want you to reverse engineer their product. Let me flip the board over again and let's take a look at the multimeter section again. As you can see here, there isn't too much input protection to speak of. You have these standard fuses for overcurrent protection and a relay for range switching, and that's pretty much it. Now I suppose we have some clamping circuitry around this section here, and here we also have a PTC. And here you can see a couple of resistors in series to form that 10 megohm input impedance. And this arrangement does allow you to distribute the input voltages across these two resistors, therefore improves the margin for high voltage measurements. While it is disappointing that we don't know much about the ICs used in this meter, I have to say the overall board design is quite clean and the assembly quality is quite decent. Anyway, that's pretty much all I want to cover in this video. So what is our conclusion? I think this meter is definitely quite capable, especially considering its price. The oscilloscope design is intuitive. Of course, it lacks some of the measurement capability you will find in a bench oscilloscope, but for hobby and field use, what this oscilloscope provides should be more than adequate. The 25,000 counts multimeter provides enough resolution and is certainly quite impressive in that regard. Of course, it has some design flaws, but none were fatal. And for a budget meter like this, you can't really ask for much more than that. Overall, for the price you pay, the ZT-703S is of surprisingly good value for hobbyists. Anyway, I hope you enjoyed this video, and if you liked the video, please remember to give it a big thumbs up and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes a video like this possible. Thanks for watching, and I will catch up with you next time.